Okay, we're back. We're doing some electrostatics, and in particular, we're doing some of the tougher problems that students tend to run into. And these would be cases where you have to find either electric fields or electric potential, not for shapes where you can use Gauss's law, spheres, cylinders, plates, but rather just like sticks, everyday objects that could have a net charge and are a little trickier to figure out. And the reason for that is the one thing that we know how to do is basically find electric fields and electric potentials for point charges. And what that would look like, let me change colors here. We know for fields, it's kq over r squared, and that's a vector quantity. And for potential or voltage, it's just kq over r, which is just a scalar. So voltage is a little bit easier to work with. So the thing is, when you have real objects, okay, note this little thing my daughter wanted to make sure that you knew that she was here. We have to set up integrals. We have to add up all the contributions of little point charges in order to get the total at some point. So the case I'd like to do, actually two cases, involves sticks. Now we're just going to get to the point of setting up the integrals. I'm not so worried about actually going through and solving them. You can look up in integral tables, plug it into an Inspire, use calculus methods to figure those out. I just want to get the setup. That's the physics part. So here's a case where we're trying to find the electric potential at a point over here, which is off the axis that cuts the stick in half. Now the stick has a total length of 2L, and we'll just say that it has a charge of big Q, okay, net charge. Okay, so how would you find the voltage? So in this case, I guess the way we can approach it would be, imagine just kind of an arbitrary point down here. Little chunk of the stick, we'll call it dq. Now that point is a certain distance away from where we're trying to find the voltage. Okay, that's the r. Now the way I've set up my coordinates here is my y equals 0 is level with the point that we're trying to find. So our variable is that vertical distance from my origin, which is the y distance. Now the x distance is a set constant, x equals a in this case. So the first thing we can say is that the r value for any point on the stick, using the Pythagorean theorem, is the y value squared plus a squared. Okay, and again, it's the y that's going to vary from point to point. So the voltage, a tiny little bit of electric potential that little point charge is creating, we can find kq over r. Now if we want to get the total voltage, we have to add up all of the little voltages. That means an integral. Now the thing is, let me go ahead and substitute in for the distance. We'll put in our square root. The integral as written right now, we can't solve. And the reason for that is, since our variable is y, we need a dy in the expression. So how do you do that? How can you write charge in terms of a distance? Well, that's where we're going to make use of ratios. As long as the charge is evenly spread over the stick, you can imagine a little, almost like a density idea. The total charge divided by the total length is just some number. Now if everything's uniform, that means that this little chunk that we're looking at has a little bit of length called dy. That's a good calculus name for it. So this ratio, dq over dy, should be the same. Okay, that's also a constant if everything's uniform. So if we solve for dq, this is what we're going to substitute into our integral so we can solve it. So what it looks like is we have our constant. We now substitute in for dq total charge over total length times dy all over our distance. And I guess the only other thing we have to do is make sure we get our limits right. We want to add all these little voltages up from the bottom of the stick. So relative to our origin, that y value is down below it. So it's negative L minus B. And the highest point, the top point of our stick, is L minus B. That's the integral that we'd need to solve. Okay. And again, I'm not going to worry about the answer for this. So now, compare what we have. That's probably the trickier of the two that I want to show here. The other one is something that I put on very similar to one I had on the test. We had a couple sticks, but we're trying to find the electric potential. We'll stick with potential for this. At a point along the long axis, okay, out in front of the stick. So again, we have a total charge and total length. At some fixed distance in front of the stick like that. Imagine a little point, a little slice of the stick with a little bit of charge. That's a certain distance away from the point, okay, an x distance. X is our variable. That's what's going to change from slice to slice to slice of our stick. What's the voltage from that little piece of charge? Well, it's k dq over our distance, which is x. If we want the total voltage, the total potential, we have to add all these little things up. Okay. Again, x is our variable. We can't have a dq in there. We'll do exactly the same trick. We'll use ratios. Total charge over total length is equal to a little chunk of charge over its little length that we can call dx this time. And as long as everything's uniform, we can do this because its ratio will be some constant. It's like a density. So that'll give us charge in terms of the little length of our little slice of the stick. So check out what this looks like. We're going to substitute in our new expressions. So we have our constant charge over length times dx all over x. Now we need the right limits on this. Well, one end of the stick, let's say, I guess let's define our origin. Maybe I'll put it at the left end of the stick. As long as you define it, we can just think of our distances from there. So one end of the stick is a total distance of L plus B away from that. And then our other end of the stick is a distance B. Okay. If we integrate this, we can pull out constants. We have dx over x as our integral. Now this one we can just do. It's nothing tricky like the other one. This will be a natural log. And if we evaluate that, looking at our limits there, we can just go ahead and write down the answer. I skipped a couple of lines of algebra. The answer isn't so important. It's really the setup. In this case, I would say that this is where you want to get. Okay? And it's this more challenging one, I guess you could say. This is really where you want to get to. And after that, then we can do the calculus. It's all math from there. But to get here, we need to know the physics. Okay? It's the same procedure every single time. We break it into point charges, we add them all up with an integral, and then we have to do this little trick here of using ratios in order to set up the integral so it's solvable. It doesn't really matter so much what the picture looks like. That's the process we'll use time and time again. Okay? The stick could be curved, it could be a ring, it could be at other locations, arbitrary locations. Even if you had weird looking shapes, zigzags or whatever, technically this is how you'd have to be able to set it up. This is the process. Point charges, adding them up. So I hope this helps a little bit. My daughter thanks you too. And until next time, we'll see you later.